All right. Hi, everyone. Good morning, good afternoon, or good evening, or whatever. And welcome to STOC session 3C, which is on privacy and fairness. So we have 4 contributed talks in this session. Just to remind you of the mechanics in case you aren't familiar. So there will be 10 minutes for each talk, roughly 5 minutes for the talk itself, and then 5 minutes for questions and answers. If you have a question, you can either type it into the chat and we'll make sure to share it with the speaker, and the speaker will be able to see it, or raise your hand and keep your hand raised until the end of the session and we can unmute you and let you ask your question live. All right, so without any further ado, Alex, would you like to share your screen?
Yes. Sorry, 1 second here. Oh, gee.
Okay, great. So our first talk is on the power of factorization mechanisms and local and central differential privacy by Alex Edmonds, Sasha Nikolov, and John Ullman. And Alex is giving the talk.
Thanks a lot, Mark. So let me just mention that today we're not really going to be discussing the central model portion of this work. We're really going to focus on the local model results. Now, the goal of local differential privacy is to release useful aggregate information while at the same time protecting individual privacy. And the local part of this is that we want to do it without relying on any trusted party. So each data point is going to be held by a distinct agent. They're going to publish it through their own differentially private mechanism. And then the final output is obtained by post-processing this transcript. Now, our main interest is in answering linear queries. So these are given by a predicate, which is just a real valued function on the data universe. And then the corresponding linear query evaluated on a data set is going to be simply the empirical average of that predicate on the data set. And often we like to think about answering a collection of such queries. So we call this a workload. And the evaluation of a workload is simply the vector of the evaluations of the individual queries. And it's useful to represent the query workload by workload matrix, which is simply at query Q and universe element X is going to be have entry Q of X. And this is nice because then we can use the histogram representation of a data set and express the query answers as a matrix product. So the query matrix times the histogram. Our notion of error is expected L infinity error. And then sample complexity is going to be defined as simply the minimum number of samples required to achieve this with an epsilon LDP, and for that specific query workload. Now, the most basic technique in differential privacy is to add noise. So we're able to obtain under epsilon LDP basically the answers to the queries plus some random noise. And this is going to witness this particular sample complexity bound, which is going to be optimal for some query workload. However, additional structure in the workload may allow for better algorithms. Okay, now we can get into factorization itself. So the idea of factorization is that to answer a given query workload, we may want to first answer a different query workload and then reconstruct the answers to the original by a linear recombination. So here we have our query workload, W. It's going to be factored as matrices R times A. And we think of A as giving a new workload of queries. So we're able to answer those using the techniques we just saw. But then to get the answers to W, we post-process these answers by the reconstruction matrix. And that'll give the answers to the original queries. Now, our modest extension of this approach considers a W tilde, which is a small perturbation of the original query matrix. Indeed, accurate answers to W tilde are going to give us accurate answers to W. So we can apply factorization to W tilde instead. And in particular, by optimizing with respect to our choice of W tilde, as well as its factorization, R times A, we're able to get this sample complexity upper bound. And the key thing here is it's characterized in terms of this gamma 2 norm, which is a well-studied a measure of the complexity of a matrix. And moreover, there's an algorithm a protocol which achieves this sample complexity with polynomial time in the size of the universe and the workload. Now, actually, the real focus of our work has been on the lower bounds. So this is our lower bound, which we won't discuss in too much detail. There is a bit of a gap between it and the upper bound. So for instance, we're missing this log factor. Nevertheless, we're able to use this to even give new lower bounds against threshold queries and marginal queries under epsilon LDP. And then let me just mention an open problem. I think the most interesting open problems here relate to the question of interactivity. So this work really only considered non-interactive LDP protocols, and it remains pretty wide open what the role of interactivity is in answering linear queries, and in particular, we wonder whether it's possible to get exponential sample complexity improvements by allowing for interactivity. And that's the end of my talk. Thank you.
All right, thank you, Alex. So now we're going to move on to the Q&A portion of the talk. So again, if anyone has a question, feel free to type it into the chat or raise your hand. All right, so we have a question from Cayman. In your talk, you mentioned that part of the lower bound is finding hard distributions for a workload queue. Mm-hmm. Can you give an idea of what these distributions look like?
Yeah, so I mean, the basic idea of the lower bound is that, so you're answering this query workload. So you have this collection of queries. Basically what these hard distributions are going to look like is you want a pair of distributions for each query in that workload. And you basically want to be able to say that that answering that particular query corresponding to this pair of distributions should allow you to distinguish between them. Now, I don't think I can really say in much more detail sort of what they look like. I mean, but they kind of they come out of these sort of geometric arguments. You know, we look at the gamma 2 norm. We express it as a dual. We use this dual then to get those hard distributions that witness the that witness this this upper bound on that for the lower bound. Yeah.
And if you'd like to discuss in more detail, we do have Slack channels for all of the papers, for which we can take some of the discussions offline. So we have a question from Clement. Is there an intermediate notion between non-interactive and interactive that could be easier to tackle for the conjecture in question at the end? For instance,
yeah,
public
sure.
coin.
So I mean, there's there are a number of kinds of interactivity. And there's been a lot of discussion of this in the differential privacy community and work on this in recent times. Basically, you have sort of the most basic kind of interactivity is sequential interactivity. So this is where everybody speaks once in sequence, and you allow their messages to depend on earlier messages. And that's different than more general forms of interactivity where you allow each individual to speak any number of times, maybe over many rounds. I mean, if at this point, like if you had to go beyond sequential interactivity to show that to show that interactivity does offer improvements in terms of sample complexity, then it would be interesting to get that in terms of even, the most general kinds of interactivity. I mean, that would be a weaker result. But then, on the other hand, if you're trying to say that it doesn't offer improvements, well, you might as well start off by trying to argue it in the case of sequential interactivity, because in that case, then that would be the weaker result. Are we still connected?
Hey, Mark, you're muted.
Sorry. Yuval, would you like to share your slides now? Yuval, you're also muted. Oh, sorry. I think I messed up the order. Sorry, Kunal. It's your turn. We don't have to respect the order. Okay, sorry about that. All right. So next we have private stochastic convex optimization, optimal rates in linear time by Vitaly Feldman, Tomer Koren, and Kunal Talwar, and Kunal is giving the talk.
Great. Can you hear me okay?
Yep.
Okay. So yeah, this is a joint work with Vitaly and Tomer, and this was work done while we were all at Google. Okay, so let me start by defining the problem we want to solve. So I think this is one of sort of a very common and basic problem in machine learning, which I'll call stochastic convex optimization. So here you have some distribution over some data universe Z. Think of these as your distribution of the distribution that you're trying to learn over. So this could be a distribution over labeled examples, for example. And you're trying to learn this distribution or learn something about this distribution using some parameter space K. For this talk, this will just be, let's say, the Euclidean ball in R to the D. And you do this learning by optimizing some convex loss function. So I guess the simplest example would be you're trying to minimize the logistic loss over your examples. Or perhaps you want to minimize the least squares loss. And you don't actually have access, you don't have the distribution D, you just have n samples from the distribution. So we'll say my data set S is some n samples Z1 through Zn, drawn independently and uniformly from this distribution D. So these are your training examples. And what you want to do is to minimize your expected loss, this convex loss L, over the population. So when I sample Z from this distribution D, this is the quantity I want to minimize. And of course, because I only have access to samples from this distribution, I'll only be able to approximately minimize it. And the additive loss I have in my expectation is what we call excess population risk. For this talk, we'll be looking at the L2 case, which basically means that my K is the Euclidean ball and my loss function is going to have bounded gradients in L2. Okay, so I guess this is a very well studied problem, has been studied for a long time and very well understood. And the right answer, the matching upper and lower bound, is something like 1 over square root of n. So I can get this excess population risk to be 1 over square root n, and because of, for statistical reasons, I can't do any better. In this talk, we'll be interested in a differentially private version of this question. So now, instead of being able to access this training data in an arbitrary way, I have to use an algorithm which is differentially private with respect to this training data. So, so think of each Zi as an example, data coming from one person. I want epsilon delta differential privacy with respect to this data set. And once again, I want to minimize this excess population risk. This is closely related to another problem that's known as empirical risk minimization, where I care only about the loss over the samples rather than over the whole distribution. And the private version of this ERM has been very well studied. There's a long line of work. And we know that the optimal access privacy risk, how much I need to pay additively because I want privacy, is something like square root d over epsilon n. D, recall, is the dimension that my parameter lies in, and n is the number of examples. So I do pay something for dimension here. So I guess there are then two natural lower bounds that exist for private SCO. One is just the statistical lower bound of 1 over square root n. The other one that's not hard to show is this ERM based lower bound of something like square root d over n. And it's not clear if these are the only lower bounds, or is there more things that happen when we do private SCO. And in a recent work with Raif Basili, Vitali Feldman, and Abriti Thakwarta, we showed that in fact the larger of these two is the right answer. We can always achieve the larger of these two lower bounds. The nice thing about this is that when d is smaller than n, let's say, then the privacy cost is a lower order term, and privacy is coming for free. We just pay the 1 over root n that comes from statistical considerations. And the main result of this work is that we can not only achieve this upper bound, we can actually achieve it in linear time by making one pass over the data set. So not only is there no price in terms of utility, there's no price in terms of computational efficiency either. We in fact give two new algorithms that achieve this optimal rate in linear time. The first one is what we call snowball SGD, which does noisy SGD, where my batch sizes kind of increase slowly as I go along. And the other one is what we call iterative localization, where we kind of iteratively find better and better approximations to the optimum solution. We also have variants of these algorithms for the strongly convex case, which has been studied in convex optimization literature. I guess one interesting open question is the non-smooth case, where we get a quadratic time algorithm, which I guess still improves over the previous best by a fair bit, but it's an interesting problem in the sense that even relaxing privacy to something as weak as sort of stability, we don't know how to do that in linear time. I guess I'll stop here and take questions.
Thank you, Kunal. We have any questions? So I have a question for you, Kunal. Regarding the non-smooth case, is there a reasonable conjecture that one can make about uniformly stable SGD algorithms that would imply a linear time algorithm in the non-smooth case?
Right. So I guess if you have a uniformly stable algorithm, then you could run that at some noise proportional to the stability of that algorithm, and then use this iterative localization idea to kind of repeatedly improve your answer. And I would expect that if we have kind of the right stability analysis for the non-smooth case, then we would be able to get the right answer. As I mentioned, this result with Christopher Guzman, and Raif Vasily and Vitaly Feldman, we study the stability of SGD for the non-smooth case, and we get some better bounds. But I think we also show some lower bounds. So SGD itself is not going to be stable, or GD is not going to be stable for the non-smooth case.
All right. We have a question from Sasha. Can you say something about what's missing to get similar results for the L infinity L1 case? For example, using a variant of your first algorithm with mirror descent?
Good question. To be honest, we haven't thought much about the L infinity L1 case so far. I think something should be doable, but yeah, I guess I don't have a good answer. Yeah, my guess would be, given that we have well, at least a couple of different techniques, one of them would actually give us some good results, but this remains to be done.
All right, Yuval, would you like to share your screen now?
Yeah. Okay.
Okay, great. Thank you again, Yuval.
Wait 1 second. Okay, do you see my screen sharing?
Yep.
Or it doesn't work? Okay.
All right, so next we have interaction is necessary for distributed learning with privacy or communication constraints. This is by Vitaly Feldman and Yuval Dagan, and Yuval is giving the talk.
Hey, okay. Yeah, so here we'll discuss why interaction is necessary in 3 models: in local privacy, bounded communication, and statistical queries. But I will give the focus on local privacy. And in general, local privacy is a model where there is a server that wants to compute a function, but the server is not trusted. So only minimal information about the users should be leaked to the server. And we have a learning setting that each user receives some IAD sample XY from some distribution D. And the goal is to learn a function that maps X to Y. And we assume non-interactive communication. And this means that first the server will send requests to all the users. And then the users will send responses. And but these responses have to preserve the privacy of the users. So they need to have a lot of randomness in them. And formally, we require that for any 2 different inputs of a user and any possible message that this user can send, the ratio between the probability to send this message given one input and the probability to send it given the other input, and this ratio is bounded by e to the epsilon, where epsilon is a parameter, and we will assume it to be constant. Now, to give some motivation for interactive versus non-interactive. So interactive model, it just allows many rounds of communication, and it's much stronger. But each interaction round can have latencies, so it can take a lot of time to implement. And that's why most of the deployed locally private systems right now, they use non-interactive communication. Yeah, and let's just discuss briefly the learning settings that we have. So first, stochastic convex optimization of linear models. And here we want to learn a linear function, and we have a convex loss. And for classifications, and the second model is classification, and here the labels are binary. And we assume that the points are linearly separated. And the goal is to find a classifier that minimizes the 0-1 classification loss. Okay, so for prior work, so there were already exponential lower bounds for non-interactive algorithms. So for convex optimization, there were lower bounds for gradient-based algorithms and generalizations of that. And for classification, there were lower bounds when the margin that separates between the positively and negatively labeled points, and when this margin was exponentially small. But it wasn't known what happens when the margin is large. And so that's for non-interactive algorithms. And for interactive algorithms, they could be made efficient. And in this work, so we show lower bounds for the non-interactive setting for both of these models. So first, for stochastic convex optimization of linear models, we show that this requires a sample which is exponential, either in the dimension or in the excess error. And for linear classification, we show that the number of samples is exponential either in the dimension or in the margin. And this exponential dependence for these settings is necessary. Is tight. There are also upper bounds. And these bounds hold also in other models, both for learning with communication constraints. And there you don't have a privacy restriction, but instead you limit the number of bits that each user can send. And secondly, for the statistical query model. And all of these models are essentially equivalent due to reductions from prior work. That's it. Thanks for listening.
Okay, thank you. So we have time for questions now. So we have a question in the chat. What do we know about private non-convex optimization?
Private non-convex optimization. Non-interactive, it should also be impossible. I mean, the same bounds should apply. For upper bound, you can have algorithms that add gradient descent algorithms that add a lot of noise in each to each gradient, and that's how you can give algorithms. But these are interactive.
Okay, anything else? So question I have for you is, so of course, giving lower bounds for statistical queries is a really nice unified method for proving lower bounds in these other models. Do you have a sense of whether you've lost anything quantitatively by looking at statistical queries, or whether there might be a more specialized lower bound argument that you could apply for local privacy or something to get sharper results?
I mean, so I'm not sure. I think for statistical queries, it's not sharp enough. And also for, so for linear models, you have this exponential dependence on the minimum of D and 1 over alpha. And that's tight for linear models, but if you think of general context optimization, then this 1 over alpha shouldn't be here. It should just be exponential in the dimension. And so I think that's the main maybe point where, yeah. So global privacy and statistical queries should be equivalent for non-interactive. There are like two-way bounds. So, yeah.
All right. So one more question from Adam. So question that applies for both Yuval and for Alex. So say we restrict the number of rounds to 2. What lower bounds are known for natural local differentially private protocols for natural problems? For instance, query release or convex optimization.
Yeah, specifically for this, yeah. Specifically for this, sorry, is anyone else though? Yeah, specifically for this, so I don't think anything is known for optimization. Even with exponentially small margin, that it should be impossible. There is no bound, even if the margin is exponential.
Yeah, so maybe let me also, can you all hear me?
Yes.
So let me also give an answer. So, I mean, there is, so actually for query release, we really don't know of really any gap. I mean, we've been giving this a lot of thought lately, trying to, Adam particularly asked if there were natural, if there were examples where the natural protocol is interactive, and we really don't know of such examples. Yeah, I mean, there are, there are related problems where where interactivity can offer some mild improvements, log factors. So, like selection is an example of that. But for query release itself, that's basically wide open at the moment, I think.
How about the case of 2-round interaction specifically? So have you thought about lower bound techniques for query release that apply to 2 rounds of arbitrary interactivity?
As far as I know, our techniques don't generalize immediately even to the 2-round case.
We have a request from Adam to change the settings of the meeting so that attendees can see the quote gallery view. Would you be able to do that, Falcon?
Yep, I just did.
Okay, thank you. All right, great. Kang-Ning, would you like to share your slides now?
Yeah, sure. Can I see this?
Yep. All right. So the last talk of the session, we have approximately stable committee selection. This is by Jihao Jiang, Kamesh Munagala, and Kang-Ning Wang. And Kang-Ning is giving the talk.
Hello, everyone. So today I will be presenting the paper Approximately Stable Committee Selection. First, we introduce the problem of committee selection. So there are N voters and M candidates. And we say a committee is a subset of candidates. And in this problem, each candidate I is associated with a weight Si, and the weight of a committee Ws is the sum of Si. And the goal is, given a weight limit K, we want to find a committee of weight at most K. So in this problem, the voters have preferences over the committees. And we assume each voter has a weak ordering on all possible committees. And the only constraint that we add is the monotonicity constraint. So if a committee S is a superset of another committee S prime, then any voter should weakly prefer S to S prime. And the model of committee selections have many applications. For example, it can be used to model multi-winner elections and to model the problem of participatory budgeting, or to model other algorithmic questions like a clustering problem, or to design caching policies. And in our problem, we consider selecting a stable committee. So now we define the stable committee problem. Given two committees S1 and S2, we say the pairwise score of S2 over S1 is the number of voters who strictly prefer S2 to S1. And given a committee S of weight at most K, we say a committee S prime blocks S if the fraction of voters who prefer S prime to S is at least the fraction of the weight Ws prime over the weight limit K. And we say a committee S is stable if there is no blocking S prime. So the idea of this definition is this. So we want every demographic of voters to feel that they have been fairly represented. And we require that they don't have the incentive to deviate and choose their own committee of proportionally smaller size. And that won't give all of them higher utility. And we require a stability, the stable committee to be fair to all subsets of voters. And the general idea dates back to more than a century ago and has received significant attention since then. And we know that stable committees may not exist, so we want to define approximate stability. And we say a committee of weight at most K is C approximately stable if for all other committees S prime, the fraction of voters who prefer S prime to S is less than C times the fraction of weights between Ws prime and the weight limit K. And in our paper, the main result is that we showed 32 approximately stable committee always exists. And the techniques we use is that we first show the existence of an approximately stable randomized committee, and then we construct a deterministic solution using this randomized solution. So that's all. Thanks.
Okay, thank you. We have time for questions now. So I have one quick question for you. This question of, this constraint that you have that the preference structures for all of the voters is monotone. Is this something that could be relaxed or changed to a different constraint? For instance, submodularity. Like, I have preferences for candidates which diminish as more candidates are added, or which are not necessarily monotone. Like if I have some candidate who I really despise, I really don't want them to be on the committee, even if there are others on the committee to balance them out.
My intuition is in that case, a stable committee may not exist, since in the definition we say that we can't have a smaller coalition to deviate from the main solution. So when the voters prefer a smaller committee, I think there may not be a stable committee in that case. So
even approximately stable.
Yeah, even like constantly approximate stable shouldn't exist.
So Sophia has a question. Is there any intuition for why the factor 32 arises?
the factor of 32 is like it comes from the analysis of our algorithm, and there are some factors of 2 and 4, so there is a factor of 32. So in our paper, we only show the lower bound of 2. So there's still a gap between this lower bound of 2 and this upper bound of 32. And the question of tightening the gap is interesting to us.
Which of these quantities do you think is closer to the right answer?
We feel the answer should be closer to 2.
Any more questions for Kangning? All right, so we've reached the end of the session. So let's, I guess, silently thank all of the speakers again for their wonderful talks. If we have the room until 12, and at 12 there's going to be a junior senior lunch session, which I hope folks are signed up for. But since we have the room until 12, folks are welcome to stay and ask questions of the panelists. If they have any lingering things they want to ask. So thank you everyone again. In particular, Yuval, did you want to ask your question?
Oh yeah. Just for the first, for Alex, if you think that it's possible to, like, what is the sample that, like, do you still have the same lower bound, or do you think it's possible to improve?
Sorry, I'm not sure I understand the question. Sorry, can you not hear me?
Yuval says he's having some issues with his video.
Oh, okay, okay. I wasn't sure if it was me.
Yeah, he says he can't hear.
Yeah, sorry, I didn't quite catch the question. So if it could just be repeated. Then.
He says you can just take it offline.
Okay. Okay. Cool.
Oh, wait. Can you talk for a second? Or wait.
I can see and hear you now.
Yeah, I don't know. I think I have an issue with the sound, so I can ask it later.
Okay, cool.
Falcon, do you mind stopping the recording now? I think we are done with the session.